Hey there, my name is Dimitrios Kronakis. My student number is 217-987-595. Today's date is March 28, 2022. Now, today I will be explaining one of the fundamental concepts about power systems. The big question when distributing power is how do we get electricity over long distances? Well, through cables, right? However, when electrons move through cables, they create heat. And that heat is power loss. Heat comes from resistance and friction within the wire. So, how do we reduce this power loss? Well, we can reduce the amount of, electrons going through the wire. The more electrons that go through the wire, the more heat is lost. So, looking at this equation here, where current is equal to the change of charge over the change of time, to decrease the amount of charges, which is decreasing the amount of electrons, we would have to decrease the amount of current. Now looking at the power equation, where power is equal to voltage times current, if we were to decrease the current, we would have to do so in a manner that would prevent change in the power, so we can have a constant power. So we would have to compensate with voltage. Now, is there a way to do this without going against power? There is. This is called a transformer. The transformer was invented in 1886, and it is made out of three basic components: the magnetic core, the primary winding, and the secondary winding. Now, the winding is just metal wires wrapped around. The physics of the transformer comes from the wires and electromagnetism. When a current goes through a wire, it creates a magnetic field going around it in the direction of your fingers using the right hand rule. Your thumb is pointing in the direction of the current. Because of the certain shape of the winding, also known as the solenoid, we can use the right hand rule to wrap our fingers in the direction of the current going around the solenoid, with a thumb pointing in the direction of the magnetic field. We can see here that the magnetic field comes out of the primary winding and into the secondary winding. Magnetic field in the secondary winding creates an induced voltage which is proportional to the number of wire turns and the magnetic flux. In this case, the magnetic flux will be somewhat constant. So we depend only on the number of wire turns. We can use this to either increase or decrease the voltage in the secondary winding compared to the primary winding. In order to increase voltage and decrease the current, we need a step-up transformer. Now the step-up transformer will have a primary winding with less number of turns compared to the secondary winding. And with a more number of turns would increase the induced voltage, which then would decrease the current and then decrease the amount of charge, and of course decrease the amount of electrons, which would be more efficient. After going through a step-up transformer, power lines carry voltages between 44 to 768 kilovolts. Now this is way too much for the average household to hold, which is why we need a step-down transformer. Now, a step-down transformer works almost oppositely compared to the step-up transformer, where the primary windings have more number of turns compared to the number of turns in the secondary winding. Now, the induced voltage would be much lower than the voltage in the primary winding, decreasing the current in the secondary winding as well. On average, households receive a voltage between 120 to 240 volts. Thank you all for watching. I hope you learned something and enjoyed.